Memory concepts. As you've seen before, there are three distinct ways of passing fields to a function. There is pass by value, pass by reference, and then pass by reference using the out keyword. Pass by value simply means you are going to make a copy of the value you wish to pass and pass it to the method in question. This has some interesting effects when passing a reference type by value, because a reference type, when you pass it by value, allows you still to manipulate the contents of that object. We'll talk about that in a little bit. Pass by reference allows the function that's being called to manipulate the contents of any variable type, including value types. This is typically used by functions that require more than one return value. Finally, there's pass by reference using the out keyword. This particular methodology allows the user to define a function that requires a parameter to be set from within the method and then passed out to the caller. Unlike ref, which has the option of manipulating the value, the out parameters must be changed by the function in which they're defined, otherwise you will receive a compiler error. As mentioned, a lot of things are very interesting when dealing with reference types, which we'll talk about in the next few slides. In .NET, memory can be visualized as being split into two segments, the stack and the heap. The stack is the primary storage location for value types. It is limited in size, and it's more efficient than heaps as the memory is directly accessible. All variables, regardless of type, are indexed within the stack. With value types, however, besides being indexed in the stack, the values are actually stored at that location. Now, the heap is actually several heaps put together, which we will talk about in just a little bit. But the heap is typically limited by the size of memory available per process on the OS. So if you have large objects, they will typically be deferred to the heap for their storage. Reference types store their contents within the heap. Remember, everything is still indexed in the stack. In other words, every field will have some footprint in the stack. However, for a reference type, what happens is, as you declare the variable, what goes into the stack is simply the reference to the heap where the actual contents of the value are stored. As I mentioned, there are actually two managed heaps for objects. Small object heaps for small objects, smaller than 85K, and multidimensional arrays that are smaller than 8K. They all go into the small object heap. The large object heap handles all other objects. On this slide, I am trying to demonstrate visually what happens in memory as variables are created and then passed to methods. As you can see, on the left we have some standard C# code, and on the right we have two grids, one which shows a sample stack and another which shows a sample heap. We're not making any distinctions between the small and the large heap in this particular instance. I'm just trying to demonstrate visually what happens when you declare a variable of type val and one of type ref. So if we declare a variable of type int called x and assign the value of 10, what happens is the CLR allocates memory in the stack. In this case, we're arbitrarily picking address 1000 where it's being stored. These addresses are strictly make-believe, made them up just for this demonstration. And as you can see here in the stack, we have three columns. We have the variable, the address, and the value. So x is stored at address 1000, and the value of 10 is placed at that location. That is actually what is stored in the stack. If we create another variable of type long called y, as you can see here, we advance the address by 4 bytes since x was an int, which takes 4 bytes, and then we store the value -15 at that location. And since a long is 8 bytes, the next address is 1012. And we store there the contents of Z. And as you can see here, Z also has the value of 10 because we assigned the value of X to Z. One thing to note, however, these two variables do not point to the same 10. They both have their own distinct copy of 10. So if I were to change X or to change Z, it would be independent of each other. Next, we start looking at reference types. As said before, strings are reference types, but they behave like value types at the time you code them. In other words, when you compare things with the equals operator, you're not comparing addresses, you're actually comparing contents. But for all practical intents and purposes, a string is a reference type like any other. So when we assign the value ABC to the string S, what happens is we find the next available address in the stack, which happens to be 1020, and then instead of storing ABC at the location in the value column, what we end up doing is allocating memory in the heap, which you can see below, and store ABC there. And again, these addresses are strictly made up. So we have the address of 200,000 stored for ABC, and as you can see, that is the value that is stored into the value column for S in the stack. So as you can see here, S is at address 1020, but its value is 200,000, which is actually an address into the heap. And as you can see here, ABC is at that address. Then we'll create two random reference types called myObject, and the declarations will, as you can see here, will be M1 equals new myObject, and then we'll do an assignment operator to assign M1 to M2. If you take a look in the stack, M1 and M2 are both given distinct locations in the stack. As you can see here, we're using 32-bit memory, so each one takes up 4 bytes of memory. But if you look at the value, remember, when we created M1, it would put its contents in the heap somewhere. We don't really care what the data is for this object. Just be aware, at address 200,016 in the heap is the data for my object. But when we did the assignment from M1 into M2, what we ended up doing was we copied the value, just as we would with any other value types. We copy what's in the value column into the new variable's address. So we ended up copying 200,016 into the stack's value for M2. Notice here they are now both pointing to the same reference in the heap. It is for this reason that is when you create two reference types, if you change the values of one and the other points to the exact same reference, it will manipulate the original as well. It's because we've only created one myObject, and they both point to the exact same one. Then notice here we have two function calls. Again, it doesn't matter what the functions are doing, just be aware the first one is expecting a by-val parameter passing technique, and the second one is a by-ref value passing technique. So when we call some value func and we pass x, we pass the value 10. But this is actually simpler than that. Anytime you call a value parameter or pass a value by value, you simply pass whatever's in the value column in the stack. So in this case, we pass the value 10. If we pass a value by ref, the next function we're passing the x by ref, notice we pass the address of the value. What actually happens on the side of the function that is being called, all of the parameters in the parameter list are created again in a local stack for that particular function. So in this case, some value func has a value of x being passed to it, so we'll assume it is an int parameter. So once we're inside the some value func, there is actually an integer declared inside of the stack for that function. So it is actually copying the value 10 into that location. So in fact, what happens is we end up with another value of x on the stack, which equals 10. So if any manipulations are made to that value, it only affects that local copy. Once the function terminates, we lose all reference to that new x that was declared specifically for the function. And the same thing happens with the sum ref func. We declare a new variable of type int in that function. However, because we pass the address of 1000, what happens is the new stack value ends up looking just like the original x. So we declare a new x in the stack, and its address is also 1000, and therefore its value is also 10. So any manipulations made to that variable within the function will also affect the original x, because both variables are pointing to the exact same address in the stack. Now, what happens when we pass reference variables by ref? Well, remember, if we pass a reference by value, we're simply passing whatever's in the value column. It doesn't matter if it's a reference type or a value type. Whenever you pass something by value, you simply pass whatever's in the stack's value column. So if we passed m1 to a function, we're passing basically address 200,016, which means in the function you've declared a new variable of type myObject and assigned to it the value of 200,016. Therefore, any changes made to that variable will affect the original because they're all pointing to the same heap address. Now, if you pass a reference value by ref, what happens is, again, you're just simply passing the address column in the stack. So instead of just passing the reference to the address in the heap, we're passing the address of the variable in the stack. What this means is we can physically change the value. In other words, we can adjust whatever that variable is and swap it with another variable completely. In other words, we can set the value passed into null, and what happens is the original variable also becomes null. So yes, by passing a reference type to a function, it doesn't really matter if it's passed by val or by ref. You can manipulate the contents, but if you physically want to swap out the variable with another, you must pass it by reference. Boxing simply refers to the technique where you take a value type and store it in an object reference type. This allows the value type to be stored in the garbage collected heap rather than in the non-garbage collected stack. When you unbox an object, it basically extracts the value from the object and creates a new value type to store the contents. In relation to simple assignments, boxing and unboxing are computationally expensive processes. When a value type is boxed, an entirely new object must be allocated and constructed. And remember, it's not just allocating data on the stack, it also has to allocate data on the heap. To a lesser degree, the cast required for unboxing is also expensive computationally. So for a few samples, if you just do one object boxing or two in a program, it's not going to hurt anything. However, if you make repeated use of the boxing technique over and over again, the amount of time it takes to create and destroy these objects will eventually add up and cause program degradation. We'll talk about garbage collection here in a few minutes. Just be aware that every time an object is removed from the heap, it actually has to wait for a garbage collection cycle for it to be fully removed and the memory reclaimed. The .NET CLR handles all managed memory allocation and cleanup. Obviously, for unsafe code, this is not the case. If you're making calls into unmanaged Win32 APIs, this doesn't apply. However, for everything you use with safe code, in other words, using standard variable types in .NET, basically all of the reference types are stored in garbage collected heaps. So the garbage collector cleans up the small object heap and keeps memory from becoming fragmented. The small object heap is segmented into 3 generations: Gen 0, Gen 1, and Gen 2. Objects are initially allocated on the Gen 0 heap and moved up progressively until it's cleaned up. The garbage collector also defragments the memory, making future allocations more efficient. So objects are initially allocated to the Generation 0 heap. When the heap is filled, the garbage collector is run. Objects that are no longer needed are removed. Others are moved to Generation 1. It is really not that important to know how big the Generation 0 heap is initially. It will grow slightly dynamically as needs are encountered. However, just be aware, every time you declare a variable that is of reference type, it is allocated in the Gen 0 heap. If the first time the garbage collector detects that the heap is full, it'll take all of the objects that are no longer being used by your program, and it will take that memory and reclaim it. All of the other variables will be kicked up into Gen 1 because they're longer lived. Therefore, after the garbage collection, Generation 0 should be clear. Now, the same thing happens in Generation 1. When it becomes filled and needs cleaning, all of the objects in Gen 1 that are no longer needed are removed, and others are moved to Gen 2. A Gen 0 cleanup is also performed, so it cascades backwards. Now remember, this also assists with defragmentation, because when a heap is cleared out, basically there's nothing left in there, there is no more fragmentation. And as objects are moved from one generation up, it will also compact those particular contents in that heap location. Eventually, the Generation 2 heap is also filled and needs cleaning. This is known as a full garbage collection. Objects in Gen 2 that are no longer needed are removed. A cleanup of Gen 1 and Gen 0 are also performed, and objects in the large heap are cleaned up. This strategy cleans up objects with short lifetimes quickly, performing full garbage collections only when necessary. So, in the large object heap, things happen a little differently with garbage collection. Okay, so any object larger than 85K and multidimensional arrays larger than 8K are automatically allocated on the large object heap. A full garbage collection is the trigger for the large object heap cleanup. Unlike the Gen 0 to Gen 2 small object heaps, no defragmentation is ever performed on the large object heap. This can lead to performance degradation over time, as it may become difficult to find memory slots for large objects. If there is not a slot large enough for an object's allocation, an out-of-memory exception is thrown by the CLR. Again, this only becomes a problem if you have objects that are very large. Most of the time, your objects that you create are going to be small and nimble objects. However, if you're declaring large arrays or you're reading very large files into string objects, those have to be allocated in the large object heap. And when you're no longer using those objects, they will be cleaned up. However, they only happen with a call to the garbage collector's complete cleanup. In other words, a full garbage collection. You can force a full garbage collection by issuing the command gc.collect. However, this is not necessarily a good thing to call, because the CLR is optimized to call these garbage collection routines when necessary. However, if you know you are creating large objects frequently and you want the memory to be reclaimed immediately after you're done using them, then yes, you would have to call gc.collect to clean out the large object heap. IDisposable is a pattern you can implement to make cleaning up your objects more deterministic than relying on the class's finalizer, otherwise known as a destructor. If you implement IDisposable, you must also implement the dispose method within your class. The dispose method provides a location to clean up memory before a garbage collection would normally reclaim the memory. So we are doing things ahead of the garbage collector, so we're not waiting on a GC collect or a garbage collection routine to actually clean up our data. Commonly, dispose works in conjunction with the object's finalizer, the tilde class name function. A finalizer is not meant to be called explicitly. Instead, a finalizer is called by the garbage collector when an object is about to be deleted. With dispose, an object can be cleaned up deterministically, then suppress the call to the finalizer from the garbage collection. Using the IDisposable pattern, you can separate managed and unmanaged object disposal. In this test, we created a class called testObject, which implements IDisposable. Notice here, because we implement IDisposable, we must have the public void dispose function that accepts no parameters. You can see that declared towards the bottom of the class. This class also has an external reference to kernel32, which is a Win32 runtime DLL. We create an extern static bool called close handle that accepts an int pointer handle. This is basically like a delegate. We're creating a function name inside C# that refers to the function of the same name in the kernel32 library. And this is the way we declare them in C# so we can call them directly. Then we have a bool variable called mDisposed. We are going to be using that to monitor whether or not this object has been disposed explicitly. You'll see that later. Then we have a SumObject variable. It doesn't matter what's in there. It is just some managed reference type that we need to dispose of. And we set it to null initially. Then we also have an int pointer variable, which is an unmanaged object. This is basically like having an object pointer to unmanaged code. Int pointer is the way we hold pointers to C++ or some other external language code that uses memory addresses explicitly. And we set this to int pointer.0. Let's jump down to the dispose function that accepts no parameters. This is the one that is implemented for IDisposable. It only makes two calls. First, it makes a call to the other dispose overload passing true. And then it calls gc.suppressFinalize passing this object. What that does is it tells the finalization queue to remove this object so the finalizer does not get called a second time. So we are able then to clean up this object and make life easier for the garbage collector. So when it calls the other dispose method, it's going to pass the value true. Okay? Then inside that method, it checks to see whether or not our class level disposed bool has been set. If we have not disposed of this object yet, what we do is we decide whether or not we need to dispose both unmanaged and managed resources. If true was passed in, then we are free to dispose all of our CLR declared objects, like the SumObject object to dispose we declared up at top, and we'll call its dispose method, assuming it actually has a dispose method. So in that case, we are disposing all of our managed resources. Then we make a call to the appropriate method to clean up unmanaged resources. Well, we have a close handle function, which we're passing the object to. That will close out the handle and do whatever is needed with the unmanaged resource. And then we set its pointer value back to 0. Once all of this is done, we set the class level disposed mDisposed variable to true. This indicates that we have disposed the object. Now, what happens if we don't explicitly call dispose, but the garbage collector detects that this object is in the finalization queue? Well, what happens then is the tilde testObject finalizer gets called, which in turn calls the parameterized dispose method, but this time passing false. So what happens in here is it checks to see whether or not it's been disposed, and in this case it still would not have been disposed because we did not call it explicitly before. The difference being, since we passed false to this function, it will not dispose of managed resources explicitly here. It'll be left up to the garbage collector since we've already gone that far. However, we still want to clear up the unmanaged resources, regardless of whether or not the garbage collector is the trigger for this disposal or we did it explicitly. So the unmanaged object is always disposed. It's only the managed object that we dispose only if we're doing it explicitly through the public dispose method. Just so you're aware, the garbage collector will call any object's dispose method if it exists.